In the previous video, we introduced a string data structure. We discussed some problems. In the end, we talked about lexicographic rank problem. Let us take a look at implementation of lexicographic rank solution, which is big O of n. So the idea was, we have a string, we see how many characters are smaller than s, we fixed all those characters one by one, there are 4 smaller characters, then we can fill rest of the 5 positions using factorial 5 ways. So after fixing s, then we move to t, we see how many characters are smaller than t, 4 characters, and then we have factorial 4 permutations for remaining 4 positions of every character. So that's how we find the lexicographic rank of a string. We count how many strings are smaller, we add 1 to it. This was the idea. How do we implement it? As discussed earlier, we make a count array, we count frequency of every character, how many times every character appears. That's the simple logic. After that, we build the cumulative count array. So for every character I, count of I has how many characters are smaller than or equal to than this character, right? Once we have cumulative count, for every character I can know easily how many characters are smaller than this. I just need to look at count of str I minus 1. That is what I do here. So now I implement this logic once I have the cumulative array. In this loop, I am one by one calculating these terms. So for computing these terms, I have pre-computed factorial n, which is n is 6 here for this string, so I have already computed 6 factorial here. So when I come inside the loop, for the first character, I need factorial 5. So I divide it by n minus 0, I get factorial 5. Now I count how many characters are smaller than this, multiplied by the factorial value. After that, I need to reduce the cumulative count for all the upcoming characters. Why are we doing this step? Reducing frequency of all the characters after this particular character. Let's see what happens when t comes. When t comes, we do not consider s as a smaller character. We consider only ring as smaller characters because we need to consider only characters which are on the right side of it. So we remove s's count from t and all the other greater characters. So that is what we do here in this particular loop. Once we have reduced the count, we iterate in the loop and move to the next character. So that's the implementation of this logic. And we keep adding these terms to the rank, right? We initialize the rank as 1 because ultimately we need to add 1 to the result. That is why we initialize the rank as 1. So this is an implementation of lexicographic rank in big O of n time. Why am I saying big O of n time? Because I'm assuming that this is a constant operation and I'm running a loop. Inside this loop, I'm doing this operation and other constant operations. So that is how the time complexity is big O of n. Let us now talk about the next problem. We are given a big string, text string, and we are given a pattern string. We need to find if any permutation or anagram of this string exists in this string at contiguous locations. So this problem is also called anagram search or permutation search. So if you take a look at this example, there is a permutation of this string GEEK, which is present here, right, and also present here at contiguous locations. So output is yes. If I take a look at this example, GKS, I have these characters present, but no permutation of this string is present at contiguous locations. So I have KS, but I do not have G, neither here or not at this location. So no permutation of this string is present in this. So I output as no. How do you solve this problem efficiently? You may pause this video now and try yourself. A simple solution is to move this pattern one by one at different locations. I put this pattern here. I count how many characters are there, what are the frequencies of different characters in this window of this, what are the frequencies of all the characters in this window of this. Basically, I do one by one match of every character. I simply call my anagram search algorithm that I wrote earlier in the first example of string problems. So I move this character then here and then call anagram search. Then I move here and call anagram search. So what is the time complexity of this simple solution? Say n is the length of this text and m is the length of this pattern. So what was the time complexity of anagram search? So if you're searching this with this, your time complexity is big O of m. And you do call this search for n minus m plus 1 possible windows. So overall time complexity of this simple solution is going to be n minus m plus 1 multiplied by m. So let me repeat the solution. What I'm doing here, I take this pattern, put it here, and simply call anagram match is our anagram function that we discussed in the first lecture, right, on string data structure. Then I move here and simply call R anagram, right? As soon as I find true, I return true overall and I get yes as an answer. So I have overall time complexity as n minus m into m. So I can remove ones and twos, they do not matter. So this is the overall time complexity, worst case time complexity of this algorithm. Can you solve this problem in linear time, in big O of n time? You may pause now. So the idea of big O of n solution is to build the count array for your pattern and build the count array for first window of your text, right? So you have the count array where you have count of G as 1, count of E as 2, count of K as 1, and similarly you have counts here, right? You compare the counts. If the count arrays match, you found an anagram of the pattern in the text. Suppose these count arrays do not match. Suppose I had something else here. I had, say, Q here, and then I had a G here. So this is present here at this location. So I tried to match the count arrays with the first window. They were not matching because I have Q here and I expect G here, right? So how can I quickly match the count arrays of next window with this window? How much time count array matching takes? It can be considered as a constant operation. So the idea is to update count array of next window using the count array of previous window rather than creating a new count array. How can we do it? We actually already have the count array for this current window, right? I remove the count of Q and add the increment the count of G, right? Which is a constant operation. So that's the idea. We make a count array for first window of the text. We make a count array for the pattern. We compare these two count arrays for the first location. If they match, we return true. Then we move to the next window. So moving to the next window, which was a big O of m operation in the simple approach, becomes now big O of 1 operation. Because what I'm doing, I'm simply removing the first character of the previous window by reducing its count and adding the next character of the last character of the current window. So this question is a mix of sliding window strategy and character count strategy that we use in string problems. So let's take a look at the implementation of this approach that I just talked about, linear time approach, big O of n, where n is the length of text. So what we do is, we initialize the count of text window as 0. We were comparing window-wise window. And in Java, it's by default anyway 0, so I do not need to write this part or this part in Java, right? I initialize the count of pattern as 0. So this is where I compute the count of first window in the text, and I also compute the count of given pattern, all the characters of given pattern. So I have the count of first window of text here, count text window, and count pattern as count of characters in the pattern. So now I run a loop from the mth character to last character of the text, and what I do is I simply compare the two count arrays. So in this rsame function that I'm not written here, I'll simply be running a loop for int I equals to 0, I is more than 256, I plus plus. If count of this I is not equal to count of this I, then return false. At the end, return true. Simply comparison of two arrays I'll be doing in this rsame function, right? So I first compare the window, previous window that I already computed here. If they match, if the counts match, then I found a pattern anagram in the previous window, so I return true. And after that, I prepare for next iteration. I remove the last character of previous window and I add the last character of the current window and remove the first character of the previous window, right? And at the end, if I did not find any matching window, I return false. Let us take a look at the next problem. We are given two strings, S1 and S2. We need to find if they're rotations of each other. So they can be counterclockwise rotations or clockwise rotations. So I can find S2 as by rotating this 2 times counterclockwise or by rotating it 2 times clockwise. So I get D here and then I get C here, right? So it can be either clockwise or counterclockwise, it doesn't matter, because if string S2 is a counterclockwise rotation of S1, then it is also clockwise rotation. We need to find if S2 is a rotation. So in this example, again it's a rotation. You can move these two A's here, right, and you get that rotation. This is not a rotation. I can't get this string by rotating some characters. So let me clarify what I mean by rotation. I take this character, move it here. Then take this character, move it after B. So these are 2 rotations. Then I move C. This is 3 rotations, right? So I need to check if S2 can be obtained from S1 by doing any number of these rotations. How do you solve this problem? So a naive solution could be, I take the first character of this string, search it everywhere in the second string, I find it here, then I do modular increment of indexes and I just check if it is matching or not. So I found A here, I reach here. I compare B with the next character, I reach the end, so I do modular increment of index, I compare C with C, I compare D with D. If they are matching till the end, I say they're rotations, right? In this example, I'll search A here, right? And I'll match next character, not matching, so I'll go to the next index of A, next occurrence of A, I'll again start searching, then next occurrence of A, and then again start searching. So this solution works perfectly fine, but if there are multiple occurrences of a character, then you can see it goes beyond more than linear time. For every occurrence, we need to check if it is completely matching or not, right? So can we solve this problem in linear time? There is really a very interesting solution for this problem. So the idea of linear solution is, if I concatenate one of these strings with itself, if I do S1 equal to S1 plus S1, and if I search S2 into this concatenated string, if S2 is present, then I say S2 is a rotation of S1. Because I have some characters matching at the end, and then some rotated character, then I bring by concatenating S1 to itself. So if it is a rotation, it must be present, S2 must be present in S1. Right? So for this, we have functions in both C++ and Java to check whether a string is present in the other string or not. I talked about these functions. In C++, we have find function. In Java, we have index of function. Find function returns a constant string : and pos if this string is not present as a substring. Index of in Java returns a negative value if it is not present. So we can use these functions. So first thing I do is I concatenate S1 with itself. Right? After concatenating S1 with itself, I search S2 into it. So if I find S2, I say that S2 is a rotation of S1. So if you're programming in Java, you will write index of smaller than 0. If it is smaller than 0, then it is not present. If it is anything which is greater than or equal to 0, then it is present. So if you're programming in Java, you will write S1 dot index of S2 greater than equals to 0. If this is true, then you return true, otherwise you return false. In C++, we have a constant to check whether it is present or not. Let us now talk about pattern searching problem on strings. So I have a text and I have a pattern. I need to find all indexes in this text where this pattern is present. So this pattern is present at index 0. This pattern is present at index 2. This is the index 2 from which it begins. Let's see this example. This pattern is present at index 3, right? It's not present here. Let's take this example. This pattern is present at index 0, present at index 1, present at index 2. How do I solve this problem efficiently? Let us now talk about naive algorithm to solve the problem. So the idea of naive algorithm is, we move the pattern to all positions of given text one by one. So I move this ABCD here at the first position first, compare the characters. As soon as I find a mismatch, I move to the next window. So at this window, I again compare. I compare A with B. I find a mismatch. So I move to the next window. I compare A with C. I find a mismatch. So I move to the next window. I compare A with A matching. I move ahead. B with B matching. C with C matching. D with D matching. I found all the characters matching. So I print this index. Right? So if you take a look at this implementation, this is the starting position of the window in the text. We start from this position. Then we move all the positions till this position. That is why we run a loop till n minus m, right? Till this position. M is 4 and n is 7, right? So we run this loop till index 3. Now, when we are at this window, at ith position of the text, we match all the characters of pattern and text. For text, we use index I plus j because we are at our ith position. After the ith position, we are matching jth character with the jth character of the pattern. As soon as we find a mismatch, we break this loop so that we can move to the next window, right? So we started this window. We found a mismatch here. We move to the next window. We found a mismatch at the first position itself. We move to the next window. And if all characters match, we print the window position. Okay, we found a match here. That is how we print all the windows. So in this example, we'll print 0, then we'll print 2, right? That's how we get all the windows one by one. So what is the time complexity of this approach? You are running a loop which is n minus m times running, n minus m plus 1 time running, and then you are running a loop which is running m times. So the time complexity of this is big O of n minus m plus 1 into m. This is the time complexity of this algorithm. Can you optimize the naive string matching algorithm if I tell you that all the characters in the pattern are different? Can you make this algorithm to work in big O of n time in this particular case? Let us see. According to this new problem, this is not a valid input because all the characters in the pattern, they have to be different. There are repeating characters here. So these two are our valid inputs in this modified problem. Now we are going to solve this modified problem in big O of n time. How do we solve this? If you notice this loop, I have removed the I plus plus part. I am incrementing I here. I do I equal to I plus j if there was a mismatch after certain matches, if j was not 0. If j was 0, if the first character itself did not match, then I run like the previous algorithm. So the idea is this: if I am doing j work extra in this loop, then I am jumping the window by j. So that's how this overall time complexity is big O of n. And how can I jump the window by j without missing any valid matches? Let's see. We compare all the characters one by one. We compare A with A, B with B, C with C. When we come to D, we see a mismatch. Now our j is 0, 1, 2, 3. We saw a mismatch at j equals to 3. So we come to the else part, and our I was 0 here when we started. Now we move this I to 3. And is this a valid move? Am I missing any potential matches? This is a valid move because all the characters in the pattern are different. So this A cannot match with this B because this B was matching with this B, right? So this A cannot match with this B. This A cannot match with this C because this C was matching with this C, and all the characters in this are distinct. So this C and A cannot be same. And it was matching with this, so this A cannot match with this. So that is the reason I can safely jump to I equals to I plus j if there are distinct characters in my input pattern. So if your pattern contains distinct characters, you can very well modify your naive searching algorithm to work in big O of n time. The problem comes when your pattern has repetitions. How do you optimize this particular case to work in big O of n time? So we have talked about naive string matching algorithm. We saw that it was big O of n minus m plus 1 into m, or for all strings. and when all characters are distinct, it was big O of n. Now there are more algorithms for string matching. I've just written few of them. There are actually plenty of algorithms. There is Z algorithm, which also works in big O of n worst case. There's Boyer-Moore algorithm. I've just written the most popular ones. So Raven-Karp is the next algorithm, but this algorithm is still big O of n minus m plus 1 into m in worst case. On average, it works better than naive algorithm. Then there is this KMP algorithm that works in big O of n in worst case, right? This is much better than these all previous algorithms. So these algorithms, both of these algorithms, they pre-process the pattern to find the matches quickly. Now there are more algorithms, more data structures rather, which pre-process the text and search a pattern in big O of m time. So when we say pre-process the text, it means that they are going to take big O of n time to pre-process the text. Now, if you have multiple queries on the same text, then every query is going to take big O of m time, whereas m is pattern length. So if you have a text which keeps changing, then you will use one of these algorithms, right? Which these algorithms or Boyer-Moore or other algorithms which pre-process the pattern, right? But if your text is fixed, say Gita, right? Gita text or Shakespeare's work. So if your text is fixed, then you can pre-process the text so that whatever a user is searching on a fixed text, every query can be answered in big O of m time. So suffix tree is not part of the syllabus in this course, but it's an interesting data structure which works this in big O of m time. Although we have trie in syllabus, and suffix tree is basically a trie of all suffixes in its basic form. Let's now talk about these two algorithms, Raven-Karp and KMP, which are better than naive algorithm. Let us now talk about these two algorithms which pre-process the pattern. So I'll quickly cover Raven-Karp because it's not used much. The idea of Raven-Karp is this: we have a pattern and a text. So we compute some hash function of this pattern, right? And we compute the hash function of first window of text. So before matching individual characters, we compare the hash functions, which are simple integer comparison. So if hash functions are matching, then only we compare individual characters. So when we move to the next window, we compute the hash function of the next window using the hash function of the previous window. So this hash function computation is done in constant time. And we again have the hash function of next window. So we compare this new hash function with the hash function of pattern. So hash function of pattern remains same because pattern is always the same. Hash function of every window changes. It rolls over every window, right? So it's called rolling hash, which we compute in constant time from the previous window hash. So the idea of constant time is simple. It's just like sliding window. We need to remove the first character from the hash function computation and add the last character of the current window. So idea is very simple of Raven-Karp. We compare the hash functions first. If hash functions are matching, then we match individual characters. So why is the worst case quadratic still, right? And why does it work better in average case? So in average case, what will happen is you will do quick integer comparisons and you will quickly decide, okay, integers not matching, let's not match the individual characters. That way you save a lot of work. But what happens in worst case? Let's say your string is A. This is your text. Let's add more A's. And your pattern is 4 A's. So you compute the hash function of the first window, you compute the hash function of the pattern, which is computed only once because we need the same hash function value every time. So I compute the hash function of first window. I match the hash functions, they're matching. So I start matching individual characters, right? They match. I go to the next window. I compute the hash function of this window using the hash function of previous window. So I have the hash function of this window, it is again matching. So I compare individual characters. Now I compute the hash function of the next window. Again hash functions match, I compare individual 4 characters. So in this particular case, you can see that it's even taking more than naive algorithm. It's doing some extra work for hash function computation and hash functions are matching every time, then it is matching individual characters. So it's actually more than naive, but it's the asymptotically it's same as naive. It's n minus m into plus 1 into m, right? So the Revenkarp algorithm, it does hash function computations, matches the hash functions. If hash functions match, then it matches individual characters like the naive algorithm. If hash functions do not match, then it simply moves to the next window. But worst case is still like naive algorithm. Let's now talk about KMP algorithm. This is really one of the most complex algorithms. Many people face difficulty understanding it, and really one of the most awesome algorithms in computer science. So what we do in KMP algorithm, we pre-process the redundancies within the pattern. We saw that if pattern has all the characters as distinct, then our naive can also work in linear time. But if there are redundancies within the pattern, that's where the problem is. So KMP algorithm ensures that if there are redundancies within the pattern, then also it works in linear time. How does it do it? It pre-processes the pattern. Let us understand KMP with an example. Let's first process this example like naive algorithm. What we will do in naive algorithm? We'll match A with A, we'll match A with A, then this A with A, this A with A. The matching we'll print 0. We found the pattern at index 0. Then we'll move this pattern here at next window. We'll again match all the characters, right? And the matching, we'll print 1. Then we'll move it to the next window. And we'll compare all the characters one by one. And we'll see a mismatch, so we would not print 2 as an output. So our output is 0, 1. Now how can I optimize it? How can I use the redundancy within the pattern to skip some matches? So the idea is this. I somehow store this information that these 3 characters are same as these 3 characters. I'll cover that later, but the information is called longest proper prefix, which is also suffix. So I know that longest proper prefix at this index, which is also suffix, is of length 3, right? So somehow I have this information that these 3 characters are same as these 3 characters. So when I match these 4 characters and when I move to the next window, I know that this is proper prefix, which is also suffix. Since these 3 characters are same as these 3 characters because they are of same pattern, and I know that these 3 are same as these 3, so these 3 have to be same as these 3. And these 3 also have to be same as these 3 because they were matched earlier, right? So I skip these 3 matches altogether. I simply match A with A, right? And that's how I optimize the searching by using redundancy within the pattern. So when I move to the next window, I again use the same logic that these 3 characters of pattern, this prefix is also suffix. I have pre-processed the pattern and I have this information somehow, right? And I know that these 3 were matching with these 3, right? So I skip these 3 matches and I compare A with B. That's how I optimize the naive algorithm. I pre-process the pattern, pre-compute the redundancies within it, so I can skip some matching of characters when some mismatch happens after certain matches and there are redundancies within the pattern. So what is this extra information that we store for a pattern? We call it LPS array, which is longest proper prefix, which is also suffix. So for this, every index of this pattern, we compute this value. What is the longest proper prefix of this substring of the pattern, which is also suffix? So longest proper prefix of first character, which is also suffix, is always going to be 0 because the prefix, proper prefix, is empty string. So proper means the string itself should not be considered as prefix, right? So when I come here, there is a proper prefix A, which is also suffix. So I get the value as 1. When I come here, I see there is a proper prefix of length 2, which is also a suffix. So I get 2. When I come here, I see there is a proper prefix of length 3, which is also a suffix. So I get the value 3. Let's take this example. First, always 0. When I come to AB, there is only one proper prefix A, which is not suffix. So I get the value 0. When I come here, the longest proper prefix is AB, but this is not a suffix. So let's try the next one. Proper prefix is A, next proper prefix, it is also suffix. So we get the output as 1. When we come to this, the longest proper prefix is ABA, but it's not suffix. Let's try the smaller one, AB. It's also a suffix. So we get the value 2. So that's how we fill the LPS array, and we use this LPS array to shift, right? So when there are matches, we know that these prefixes, matches, suffixes also match the input string. So this will anyways match and I can jump that one, right? Let's take this example. First always 0, longest proper prefix 1, also suffix 1. Longest proper prefix AA, also suffix. Longest proper prefix AAA, not suffix. AA, not suffix. A, not suffix. 0. So A is the longest proper prefix, which is also suffix. AA is the longest proper prefix, which is also suffix. You can try the bigger ones. If you try AAA, it will not be a suffix, right? Longest proper prefix, which is also suffix, 3. Here, again 3, right? Not 4, because the 4 length is AAAC, not matching with the suffix. AAA is matching with this AAA. Here, 4. Longest proper prefix, which is also suffix. Let's take a distinct character string example, A, B, C, D. So when all the characters are distinct, you will have 0, 0, 0. So this works like naive algorithm, right? When all the characters are distinct, you can jump the window like the naive algorithm that we discussed, right? If there are no redundancies within the pattern, you work like the optimized naive algorithm in the KMP, right? Because at every position, there is no proper prefix, which is also suffix. So in this video, we talked about some more problems on distinct data structure. We talked about naive string matching. We talked about naive string matching algorithms time complexity, which is quadratic. Then we saw that if I remove redundancies within the pattern, then naive string algorithm can work in linear time. Then we talked about Raven-Karp algorithm, which works better on average, but still worst case, like naive, even does more work than naive algorithm. Then we talked about KMP algorithm, which works in big O of n time in worst case. And the idea of KMP algorithm is to pre-process the redundancies within the pattern so that you can jump the window by more than 1. Then we also talked about suffix tree, which is a data structure. When your text is fixed, this data structure allows you to search multiple patterns on the same text in time complexity big O of m, which is much better than KMP or any other algorithm. But the problem is your text has to be fixed. So this suffix tree works the best if your text is fixed. If your text is changing, then you can use KMP algorithm to work in big O of n time.